Hi everyone. So I hope that went well. So this next chapter will be on functions of more than one variable. Up until now, when you see a function, right, it's a function of one variable, right? And yeah, don't get confused with what we've just been doing, which is a vector function, right? A vector valued function, which is still of one variable, right? The one variable is t. Okay, so it's a function that might have more than one component, right? It can have two components, x and y, or it can have three components, x, y, and z, right? But it's still a function of only one variable, one parameter, which we usually call t, although we can also call it s, right, for the arc length parameter, right? So these are examples of functions of one variable. And that's all we've seen so far. So we can have a function now of two variables. So z will be the dependent variable, and x and y could be the independent variables, right? So this is a function of two variables, x and y. Or you can have a function of three variables, in this case x, y, and z. So those are the independent variables. The dependent variable, we'll just go backwards. We'll call it w, let's say. Right, so here we have a function of three variables. And of course, you can have a function of four variables, right? Say u could be a function of w, x, y, and z. Right, and we're not going to deal with those all that much, maybe once or twice. We might see something like that. And of course, you can go on. So at some point, it sort of gets ridiculous to, just use letters. Suppose you have a function of, 100 variables. You're going to run out of letters pretty quickly. So in cases like that, you would simply use the same letter, say x, but then you would have subscripts. So x1, x2, x3, and you keep going up until however many independent variables you have, let's say 100. Right? But again, we're not going to deal with that at all. This is more for a linear algebra type of question. And of course, you can also have a function of infinitely many variables, but that's a few years off. That's a course in functional analysis, right? So in this class, we're not going to deal with these, so you don't have to worry about that. And even the four variable ones are not going to come up very often. So it's mostly two or three variables, right? And as far as examples, you've seen plenty before, right? So if you just draw a rectangle, right, and you have the length and the width, and you want to calculate, let's say, the area of the rectangle, you need to multiply the length times the width, right? So you can think of area as a function of two variables, both L and W. In this case, it's just the product of L and W. Right. But you can also talk about the perimeter, and that's also a function of two variables, L and W. In this case, it's 2L plus 2W for the perimeter, right? Right. And for three variables, of course, you have your box. Let's say it's a rectangular solid. Right, so you have length, width, and height. So for the volume, you just multiply length times width times height. So you can think of this as a function of three variables. Right? Right, so we're all familiar with that. And some of you, again, if you've had physics, you might be familiar with work. It's just force times distance. Right, so work is a function of two variables, let's say force and distance. Again, it's just the product. Although, yeah, we have talked about this very briefly. I think way back when we talked about the dot product, right? Remember, work in that case was the force dot product with the displacement. So if the force and the displacement are not in the same direction, right, then you have to take the dot product. Right, and so then it becomes a more complicated function. But you can think of it as a function of three variables now. you can think of it as a function of the magnitude of the force, the magnitude of the displacement, which is the distance, right? And also the angle theta. So in that sense, work is a function of three variables if you can vary each one, right? So if you have a variable force, a variable distance, and you can change the angle too, right? Right. And, you know, it's maybe less familiar examples if you haven't had physics yet. Maybe you haven't seen the ideal gas law. Actually, I'd rather do this version, where K is Boltzmann's constant. So, for example, if you want to solve for pressure, P, it would be K times N, those are constants, times T divided by V. And so you can think of this as a function of two variables, T and V, right, where K and N are constants. Well, N is the number of molecules, right? And if you allow like an open box where you can change the number of molecules, then you can treat N also as a variable. But K is definitely a constant. K cannot be changed. All right, so there's plenty of other examples, right? You know, voltage is current times resistance. This is Ohm's law. If you've had physics 2 or electromagnetism, so voltage depends on, is a function of both I and R, current and resistance. All right, so again, there's plenty more examples, and we might see a few of those later. For now, just the idea that you have a quantity, say Z, that depends on two things, X and Y. Or you have a quantity W that might depend on three things, say X, Y, and Z. Okay, so if you're not familiar with, you know, Ohm's law or work, just think of area or perimeter or volume, and these definitely depend on more than one quantity. Okay, so the important thing about a function of, let's start with two variables, X and Y, is that the domain is not just a set of numbers, right? The domain is an entire collection of points in the XY plane, right? So it could be, for example, this set of points here, right? Right? I mean everything inside here, right? Could be, yeah, could be the domain, D. Right? And then the range is just a set of real numbers, E, right? So yeah, if you have a set of, right, if you have for each point X and Y, right? So let's say this point right here in red, this has coordinates X and Y. So for every such point in D, there is a real number Z, then F is a function of both X and Y, right? So X and Y being the independent variables, and then Z depends on X and Y, so Z is the dependent variable. Right. So, and this is the only situation for which we can talk about the graph, right? So we can graph a function of two variables. But as we'll see later, we cannot graph a function of three variables, right? So the way we graph a function of two variables, and maybe we should just look at an example about just x plus y, right? So we have a function z, which is just x plus y. And how would we graph that, right? So here's the xy plane, right? And so the values then will be on the z-axis, right? So for example, if I plug in, let's say, x equals 2, y equals 3, then z will just be 2 plus 3, which will be 5. So I go 2 units out on the x-axis, 1, 2, 3 units out on the y-axis. So this point here is the point 2, 3 in the xy plane. And then we go up 1, 2, 3, 4, 5 units on the z-axis, right? So right about here. So this is the point 2, 3, 5, and that is an actual point on the graph. Okay, now it's just one point, right? There's many others. In this case, we're assuming the domain is the set of all points in the xy plane. So the set of all points xy in R2, in the xy plane, let's say. Right. So obviously this is not the graph. This is just one point on the graph. So to do the graph, let's say this is the xy plane now, and then this is the z-axis. So to graph this object, and this is going to be a surface a two-dimensional surface in 3 dimensions, right? So if you just look at what happens when, say, x is 0, right, you just get 0 plus y, or y, right? So the trace, right, is just this straight line here, z equals y. And you could do the same thing with y equals 0. You just get x. So as you move along the x-axis, right, this also goes up like that. And so what you're going to end up with is this plane here, right? Or at least this part of the plane, right? This is just a portion of the plane. So yeah, the graph of this function, f of x, y, equals x plus y, is a plane in space. Right. And in fact, we talked about that in chapter 11, right? Z equals x plus y. If you subtract z from both sides, you get the equation in standard form, z plus y, x plus y minus z equals 0. So that's the standard form of the equation, right? A is 1, B is 1, and C is negative 1, right? And D is 0. There's no D here, right? And when D is 0, that just means that the plane passes through the origin. So the origin here is one of the points on the plane. Okay. So of course, this is just a starter example, right? The functions can get more complicated from there. So for example, I'll call it g of x and y. This could be x squared plus y squared. And the graph of that, as I say, this is the x-axis, this is the y-axis. Pretend that's the z-axis, right? Right, and this is something you've seen before as well. Z is equal to x squared plus y squared, right? This is going to be a paraboloid. So it is one of the quadric surfaces, right? So here's one parabola, right? And then here's the parabola going the other way. Oh, I can't quite get that right. Yep. So it's a circular parabola. So these traces here are just circles, right? But yeah, so this is the surface of a paraboloid. And again, we're assuming that the domain here is all points in the xy plane. Right? So in other words, x and y can be any real number in the xy plane. Right? We can restrict the domain, right? Let's suppose we want the paraboloid only to go to a certain height. Right? So yeah, the paraboloid goes up forever here, just as a parabola would. But let's suppose we want to make, let's say, a bowl-shaped object, something like this. Could do a little better than that. Yeah. All right, close enough, right? So in other words, we want this top piece here to end. So let's say that the height here might be, z is equal to 9. Right? We don't want to go above 9. So remember what z equals 9 is. This is just a circle, right? So for this, the domain would have to be the set of all points in the xy plane such that, right, x squared plus y squared would be less than or equal to 9. Right, so what would that be? That would simply be the disk of radius 3 in the xy plane, right? So something like that. So as long as x is any one of these points, the x and y is one of these points here, right? Then the z will be less than 9, less than or equal to 9, let's say. Make sense? Okay, so yes, you can always restrict the domain further. And in fact, in some examples, of course, you have to. So in this example here, let's say f of x is equal to the natural log of x times y. Okay, so I'm not going to try to graph this one. If you want to know what the graph looks like, graph it on your favorite graphing program, like Desmos or Wolfram Alpha. So feel free to use those, websites or software or apps or whatever to graph these if you want a picture of what it looks like. But I just want to find the domain. What's the domain of this function here? Okay, so it's going to be a set of points, x and y, right, in R2. Well, you don't have to say that it's in R2. We assume that. Such that what, right? So can x and y be any real number? Well, if you remember anything about the logarithm function, right, logarithm of x as a function of one variable, right, had the domain that x would have to be positive, greater than 0. So if you have two variables, x times x and y, right, so we have x times y, it stands to reason that x times y now would also have to be greater than 0, right? So what's true for the one variable case sort of carries over to the two variable case. So where's x times y greater than 0? Well, let's look at the xy plane. Certainly, a positive times a positive is positive, right? So you can be anywhere in the first quadrant where both x and y are positive, right? But a positive times a negative would be negative, right? On the other hand, a negative times a negative would be positive. So you can be anywhere in quadrant 3 as well, right? And this just keeps going. Right, you cannot be anywhere in quadrant 2 or quadrant 4 because that's where x times y would be negative, right? You can also not be anywhere on the x-axis because then y would be 0, right? Remember, you cannot take the log of 0. Log of 0 is undefined. And likewise, right, x can't be 0, so you can't be anywhere on the, this is hard to do, a vertical line. You can't be anywhere along the y-axis either. Right? And you certainly cannot be at the origin, right? So you can be in the first quadrant, quadrant 1, or quadrant 3, but nowhere else. So how can we write that? Well, the easiest thing to do is just give the condition. Just say x times y is greater than 0. Right? So that would be the domain. What would the range be? Well, if you remember, the log function has range all real numbers, so the range would indeed be all real numbers, which we can denote capital R. Or if you don't like that, well, yeah, boldface R, right? So the range is just from negative infinity to infinity. Yep, right. And the range for the function g up here for the paraboloid, well, z would have to be greater than or equal to 0. So then the range would just be the set of numbers x, right, such that x is greater than or equal to 0. Oh, sorry, z. Let's not use x, right? X is in the domain. So z in R such that z is greater than or equal to 0. Right. In other words, an interval notation just from 0 to infinity. Okay, so some pretty good examples that should give you the idea, right, that when you do graph a function of two variables, you get a surface in space. Okay, let's go back to our first example. F of x and y is just x plus y. And, right, we already did this example where we plugged in 2 and 3, and of course we get 5, right? You can plug in, let's say, -1 and 4, and you get 3. You could plug in 0 and 2 and get 2, and so on, right? Or you could plug in 2 and 0 and also get 2, right? Yeah, so obviously this is not, 1-to-1 in that sense. So another way to think of the function here is that each point in the xy plane gets a different value, right? So if you're at the point 2, 3, this point here, the value is 5. If you're at the point -1, 4, I have to go up one more here, then the value here is just 3. If you're at the point 0, 2, the value there is 2, and so on. So every point, you can think of, right, every point here has a different value, a different number. So here, this would be -2. The origin, of course, would be 0 plus 0 is 0. This point down here would also be 0, right? This point would also be 0, right? So -1, oh, I'm sorry. No, that's right, that's right. -1 and 1 is 0, -2 and 2 is 0, and so on, right? This would be -2, right? And then this would be -4 here. So every point has a different value, right? These are z. These are the z values, right? These are all equal to z here, right? So every point, you associate every point with a different value, a different number, okay? So this is an example of what's called a scalar field. Right? It's a field because every point, right, you can think of the xy plane as just a field, right? And the field has a value, in this case just a scalar, a real number, right? Like 3 or 5 or 2 or 0 or any, right, any real number essentially. Right? And I'm just picking nice numbers, right? You can also do, oh, how about this point right here? Right? So I'm plugging in 3 over 2 for x and 1 for y, and you're going to get 5 over 2, right? Or 2.5, right? So of course you can get decimals as your values as well. Right? So yeah, pretty much any real number could be a value of at a given point. Okay, so right, so again, you can also think of the graph as the plane, right? As the plane z equals x plus y, and then these are the sort of the values on the plane. And in fact, what you can do is notice that at every point on this line here, which I guess I'll do in blue, the values are all the same. They're all equal to 0, right? And if I draw this line here, oops, oh no, I think that's right. I just missed that other point. Right, on this line here, z is equal to 2. Right, on this line here, it's equal to 3, and so on. Right, and then way down here, this line, so you can see they're all parallel lines. Here z would be -4. Right. So yeah, so right. So these straight lines, and they don't have to be straight lines. In other examples, they could be circles or curves in general. Right. Right. So every point on these lines has a constant z value, right? Or you can think of it in terms of the plane as a constant altitude, a constant height above the xy plane. Okay, and if this represented something like temperature, we'll talk about that in a second. Temperature is a good example of a scalar field. Right. So temperature is a nice example. You can imagine if you're standing at this point, it's 2 degrees. If you're standing at this point, it's 5 degrees, and so on, right? So the temperature varies with location. If you think of a map of the United States, and in the city of New York City, you have one temperature. In Los Angeles, you'll have another temperature. In Chicago, you'll have a different temperature. So every location has a different temperature, right? So that's a good example of a scalar field, right? Right. And so those lines, they don't have to be lines, but those curves where you have the same temperature, those are called isotherms, because every point has the same temperature. So, all right, so yeah. But this is going to be important when we get to a function, say, of 3 variables. So for our first example, let's suppose w is a function of x, y, and z. And we can make it something simple, 2x plus 3y plus 6z. Okay, so here the domain is the set of all points x, y, and z in space, right? So in R3. So now we have our x, y, and z space. So I can take an example, 1 point. So let's say x is 2, y is 3, and z is 1. So, oops, that's right about here. So 2, 3, 1. So what's the value at that point? What is w at that point in space, right? Well, plug it in the function, right? So x is 2, y is 3, z is 1. We get 2 times 2 plus 3 times 3 plus 6 times 1. So 4 plus 9 plus 6 is, I want to say 19, yeah? So the value at that point is 19. If you think of this as temperature, right, we're at 19 degrees at that point. Okay? So, yeah, so that's the idea. If you pick a different point, let's say x is -1, y is 4, and z is 2. Let's see what happens. You get 2 times -1 plus 3 times 4 plus 6 times 2. So you get -2 plus 12 plus 12. So that's 22. Okay. So plugging in different points gives you different values. Right. So wherever point this is at, the temperature is 22, or the z value, or sorry, the y, the w, right? W is 22 here. So, yes, so w equals 22 at this point. At this point, w might be, 78. At this point, w might be -45, right? So different points give you different values. So this is also a scalar field, but now it's a field in all of space. So yeah, we can't graph this. We can't graph this function. At least I can't do it. I don't know how to do it, right? And if you think about why, so we have our x-axis, we have our y-axis. These are perpendicular, right? And then you have your z-axis is perpendicular to both x and y. All right, so now we need a w-axis. So our w-axis would have to be perpendicular to the x-axis, the y-axis, and the z-axis. Right, good luck. Yeah, there isn't any, right? See, we only live in 3 dimensions. If we lived in 4 dimensions, we could graph this function. But we only live in 3 spatial dimensions, right? We can go left or right, we can go in and out, and we can go up and down. Right, we don't have a description for a 4th dimension, right? Right. So yeah, that's why we cannot graph functions of 3 variables, right? We can graph a function of 2 variables, and it's a 3-dimensional object, right? It's a 2-dimensional surface, but you need 3 dimensions to graph it, right? right? So if you want to graph a paraboloid, right, you have to do it in space, in 3 dimensions. Or, you know, think of this as the, I know it's 2-dimensional, but it's the illusion of it, right? If you look at a bowl, right, it exists in 3 dimensions. So, yeah, so the best way to think about these functions of 3 variables is to just think about the scalar field, each point having a different value. Okay? And somewhere in space here, right, at a given value of w, let's say w equals 22, all points with w equals 22 will be a surface, not a line like it was in this example. It'll be a surface. And in this case, it'll just be a plane in space. Right? How do I know that? Well, if I set this equal to 22, right, notice what I get. I get the equation of a plane. Right? In the standard form, we might want to subtract 22 from both sides to make it equal to 0. But this is the equation of a plane, right? ax plus by plus cz plus d equals 0. Right? So, right, and that's only when w is 22. If w is 78, right, you'll get a different plane. You'll get a parallel plane, but it'll be a different plane. Okay. So let's look at one other example. Suppose w is, I'll call it g of x, y, and z, x squared plus y squared plus z squared. Okay. So we're not going to be able to graph it. However, we can think of the scalar field here. And in particular, let's look at the surface of constant w. Right? The isotherms, if you will. The surface of constant w. Right. So if you're thinking about this as temperatures, right, what points have a common temperature, have the same temperature? So first of all, let's pick a w. How about w equals 1? So where is x squared plus y squared plus z squared equal to 1? Right, and you should recognize this. It goes way back. It is a surface. It's a sphere. Right? It's just a sphere of radius 1, right? So the unit sphere. Okay. So if w is a different value, let's say 9, z squared, that's also a sphere, but now the radius is 3 instead of 1. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So it's still a sphere, it's just a bigger one. Right? So yeah, the bigger the w, the bigger the radius of the sphere. Right? So of course, you can just think of w, right, as being the square of the radius, right? So when you go out 3 times as far, right, w is, right, 3 squared, or 9. Right? So on the yellow sphere, w is 1, and on the green sphere, w is 9, right, not 3. It's not the radius, it's the square of the radius. Right. If you just wanted the w to be the radius, well, you can do that, right? You can have a different function. So I'll call it u instead of w, right? So h of x, y, and z. You can make it the square root of x squared plus y squared plus z squared, right? And now, right, u would be r, would be the radius, right? So yeah, here r would be 1, and here r would be 3, or yeah, u would be 3. U and r, same thing. I'm using u as the value of the function, but it also happens to be the radius of the sphere. Okay. So yeah, you can think of this function here as just the distance from the origin, right? This is the distance from 0, 0, 0, right? And it's positive, right? You can't get a negative value of h, of u, right? The radius has to be positive, or at least non-negative, right? Yeah, it can be, of course, it's 0 at the origin, but then everywhere else it's positive, right? And so g is similar, but this is going to be the square of the radius, right? Or the square of the distance from the origin, right? Which means it increases more quickly, right, than just the distance itself. Okay, right, so in any event, these are also scalar fields. Every point in space has a different value, different temperature, right? So, yeah. So, for example, if I plug in, I wanted to do a nice one, but it doesn't matter, right? 2, 7, and -3. If I plug that into the function h, I get 4 plus 49 plus 9 under the square root. So square root of 62, I think. Yeah. So, right, and so that's the w value, or sorry, in this case it's u. Right. Or the radius, right? That's how far, this is the distance from the origin. Right? So we know that, right, this point, 2, 7, -3, is the square root of 62 units away from the origin. Right. And then w, of course, would be 62. So w at the same point will be 62. Sorry, that x is a little bit out of its way here. Instead of the square root of 62, right? It's the square of the distance. Okay, so those are functions of 3 variables. Yeah, I've been calling them isotherms. These surfaces here, the spheres, right? These are more generally called level surfaces, right? Because they're the surfaces of constant level, of constant w or u. Up here, when we did these lines, I call them isotherms, but that's in the special case of temperature, right? That's only if you're dealing with temperature. More generally, these are called level curves, right? And I know they're lines in this example, but for a paraboloid, for example, they would be circles or ellipses in general. So these would be the level curves for the function, say, x squared plus y squared, right? Because these equations are circles, right? So those would be the level curves for a paraboloid. So I hope that helps. Right, and so there's really not much to this section. It's just getting used to the notation, to the idea of a function of more than one variable, 2 or 3 variables, and then, figuring out their level curves, or in this case, level surfaces, but not, generally not even trying to graph them, right? So what would be the domain, for example, of this function of 3 variables here? So, right, you remember square root functions, say g of x, right? X has to be non-negative, greater than or equal to 0. So what's under the square root here, right? 25 minus x squared minus y squared minus z squared, that has to be greater than or equal to 0, right? Cannot be negative. I mean, if you allow it to be negative, you're going to get imaginary numbers for w. And we don't, right? So in this course, we're pretty much ignoring imaginary numbers, right? We're just dealing with real numbers. So if you solve this inequality, you get x squared plus y squared plus z squared is less than or equal to 25. So, right? So what points are those? Well, if you draw the x, y, z space here, right? So if the less than or equal is throwing you off, why don't we just make it equal to 25? We know what that is, right? That's a sphere of radius I was going to say 25, but no, the radius is 5, right? 5 squared. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 5. Right. Well, let's try that again. All right. Bit sloppy, but okay. So here's your sphere of radius 5, right? Right. But that's the boundary. That's the farthest you can go out, right? So how do we interpret the less than or equals? The less than or equals means everything inside, right? If the radius is less than 5, then that satisfies this inequality. So anything inside the sphere here is in the domain, right? So, right, so again, I mentioned this, I think, very early on, that the sphere, right, is the surface of a ball, right? So everything inside the sphere, right, the three-dimensional part is the ball. And the sphere is just the outer layer of it, the surface, right? So the yellow is the sphere, and what's inside is the ball. So essentially the domain here is just the closed ball of radius 5. Right. Oh, right, centered at the origin. Right, so the center is the origin. Obviously you can have a ball of radius 5 somewhere else, but in this case it's centered at the origin. So it's just a set of points, x, y, and z, in space, right, such that x squared plus y squared plus z squared, is less than or equal to 25. Okay, so, yep. Either way, that's the domain. Again, this is the more mathematical description of it. If you say closed ball of radius 5, centered at the origin, it's the same thing. If you're wondering what does it make it closed? Why is it closed? It's closed because it includes the sphere itself. It includes the outer layer. And we know that because it's less than or equal to 25. Right? If, on the other hand, if I just write the set of points x, y, z in space, such that x squared plus y squared plus z squared is less than 25, right, but not equal to 25, this would be an open ball of radius 5. So open ball just means it includes the solid part, but not the surface, right? You're essentially just getting rid of the outer layer. You're just peeling off the outer layer, the surface. So there is no surface, right, of the ball. There's just what's inside the ball, right? So we refer to that as the open ball if it does not include the surface. The closed ball does include the surface. And it's just a matter of whether you have the equal sign or not. Equal sign means you include the surface. You have a closed ball. A strict inequality where there's no equal sign means it's an open ball. You do not include the surface. So this is the terminology that will come up every so often. But that's it. There's really nothing else to this section. It's just getting used to functions of 2 or 3 variables. And if it's 2 variables, you could graph it, although I'm not going to generally ask you to do that unless it's a very simple surface like a sphere or a plane, right? Maybe a paraboloid if you can sort of get used to graphing a bowl-shaped object here, right? Something like this. But nothing more complicated than that, because these surfaces can in general be very complicated. But that's why we have graphing programs like Wolfram Alpha, Mathematica, Maple, MATLAB, right? Pick your favorite, rather expensive software that you can use to graph it. Wolfram Alpha will do it for free, but don't expect anything great out of it, right? It's I think if you look in the link of 11.6, I gave you a link to a very good program that will graph three-dimensional surfaces, two-dimensional surfaces rather, and you can reorient it, look at it in different ways. So yeah, your results may vary depending on what type of software, what type of app you're going to use to graph these things. But by hand, just on pencil and paper, you can graph a plane, right? Graph a plane, right? Or a sphere, or a paraboloid, but not much else besides that. Okay, so that's it for this section. Very quick section.